Good afternoon, calculus class. So I would like to talk about 2.8 today. So the derivative as a function. So again, derivative, that just considered the instantaneous rate of change of the function. So recall that f prime of a from the previous sections. So we do have limit of f of a plus h minus f of a over h as h approaches 0. Or the other form that is considered f prime of x. So it's also limit, but it's f of x plus h minus f of x all over h as h approaches 0. So one thing that we notice, so for the theorem, so if f is differentiable at a, then f is continuous at a. So if the function is differentiable at the position, so that means the function must be continuous. But now, what about the converse statement of this? So for the theorem, well, theorem, that means it's something that's being proved already, so it's always true. But what about the converse statement of this theorem? So let's say that if f is continuous at a, so what happened with the function? Is that always considered differentiable? Then f is differentiable at a. What about the converse statement? Is that always true? Sometimes true? Well, we're going to find out. So for the theorem, it's always true, but the converse statement of this theorem, it's not always true. Well, why is that? Okay, so now here's the reason why. So you see that in the next page. So 3 cases for f of x not to be differentiable at x equals a. Now for the first case here, so the function is actually continuous because that the limit from the left-hand side is the same as the limit from the right-hand side at a. And also the point is defined here at a, so it's continuous. But somehow this one is not differentiable. Okay, so I'll talk about that in a minute. So sharp turn. As you can see that the derivative for this curve right here, it's considered positive. But somehow the derivative of this second curve right here, it's considered negative. See that the slope here is all negative, the slope here is all positive. Okay, so that's why the function is continuous. It doesn't guarantee that's always differentiable. And then what about for the piecewise function? If that's a jump discontinuity functions, also the function is not differentiable. Well, because that is considered discontinuous. If the function is discontinuous, well, the function cannot be differentiable. Another thing is that it's not considered differentiable because that the vertical tangent. So imagine that the slope of this line here, what is that? It's undefined, so that's why it's not differentiable at a. So 3 different cases that the function is not differentiable. So the sharp turn, jump discontinuity function, vertical tangent line. So those are the cases you'll see that the function it's not differentiable at x equals a. So use the given graph to estimate the value of each derivative, then sketch the graph of f prime. So here's the function of f of x. And now let's find out f prime of -3. So at the position of -3 here, so we want to find out the rate of change, the instantaneous rate of change. So one thing that you can do, you can always set up the tangent line, and then you can find out the rise over run here. So just count it, 1, 2, 3, and then 1, 2, 3, 4. So rise over run, so this one would be considered 3 over 4. So again, once you extend the tangent line, you'll see that, so you want to measure that the distance from corner to corner, rise over run. So rise up 3, run 4 units to the right, so 3 over 4. And now what about the derivative at -1? At -1, so you see that it's a flat, it's a horizontal tangent. So that means the slope is always considered 0. And then f prime of 0, what about the slope right here? Once again, rise over run, so count the grids. 1, 2, 3, 4, 5. And then about 2 units to the right. So it's -5 over 2. Or -2.5. So 3/4 is 0.75. And then this one is -2.5. And now what about the slope at 2? So right here, once again, it's a horizontal tangent, so that's why it's what, 0. And now what about f prime of 4? So f prime of 4, so count it, 1, 2, 3, 4, right up here. So again, rise over run, so 1, 2, 3, 1, 2, 3. So the slope is about what? 1. And now we just want to plug in those slope for each position. So at -3, the slope is 0.75 right up here. Okay. And then at -1, the slope is 0. And at 0, the slope is -5/2. So -5/2. So -2.5. So -2.5. Somewhere right here. And now let's see what else. F prime of 2 is 0. Okay, so going back to the x-axis, the x-intercept. And then F prime of 4. 1, 2, 3, 4. So it's right here at 1. So once you connect those dots, so what do you notice? So it's kind of like a bell curve. Okay. So this one basically that just shows the slope of the graph, the original function. Probably want to extend this one a little bit further. Okay, so now let's see what else that we have. So sketch f prime from given f. Okay, so what we have right here. So again, this one is just the original function. Okay, so they're all given with the original function. Now we want to sketch the graph with the derivative. So at 0, it's considered -1.6. So count it, rise over run. So it's about -1.6. So -1.6, which is over here. And then at 2 here, so you can see that it's a horizontal tangent. You try to make the horizontal tangent line here. So at 2, so 0. And then at 3, and the slope, let's count it, rise over run. 1, 2, 3, 4, 5. 2 over to the right, or 2 over to the left. Down 5, 2 over to the left, so +5/2, so +2.5 at 3. So +2.5. And then the slope here at 5. Again, rise over run. So 1, 2, 3, 4, 5. So it's also about 2 units to the right. So it's -2.5 at 5. So -2, -2.5. And then here at 6. So the slope is considered 0. Again, if you just make the horizontal tangent, so the slope here is 0. Again, make sure that you're matching with the position. And then what about at 7? Well, here at 8. Count it. The slope, rise over runs. 2 over to the right. 1, 2, 3, 4, 5. 2.5 again at 8. Again, so once you're done with this, so just simply connect those dots. So the slope here is all considered negative because that's declining. So negative, that means for that f prime of x is underneath the x-axis. So simply just connect them all together. So another way that I can check this, you can always check that the power. So it's 1, 2, 3, 4, 4 different changes. And this one's only 1, 2, 3. 3 changes, increasing, decreasing, increasing. And then the power of the derivative, it's always considered 1 degree less compared to the power of the original function. And now what about this curve right here? As you can see that the curve here, so let's say at this position, it's almost getting close to 0 because it looks like that's a little bit flat. So at -2 here, it's almost considered 0. I would say that it's somewhere close to 0. And then the rest of the slope here is actually getting smaller and smaller and smaller. It's all negative. So if that's smaller and smaller and smaller, it's all negative. So it's going to be a curve like this. And now, one thing that you need to watch out here, the sharp turn. So what happened at the sharp turn? So at this position, we got 1, 2, 3, 4, 5, at 5. So that means it's a vertical asymptote for the derivative, because that's not differentiable. So for the graph here, so this one's getting close and close to the asymptote. It's all negative. Now, what about the other part of the graph right here? So this one is all positive. And now this one's getting closer and closer to 0. So the slope here is getting smaller and smaller with a positive number. So that means the slope here is actually considered declining. Going this way. Okay, so that's how you figured out the slope. Or the instantaneous rate of change. Okay, so now let's see what else that we have for the rest of this. So find the derivative of the function, state the domain of the function, and then the domain of its derivative. Well, the domain for the function here, so as you can see, that's a combination of linear and square root. So one thing that we notice, square root, it's always considered a half sideway parabola. So the derivative, well, we're going to find out that later, but let's find the domain first. So the domain for this one, I would say that is from 0 to infinity. And now the way to find the derivative, so we take the limit. We can use the A form or we can use the H form, depends on which way that you like. Okay, so normally the way that I would like to do it, I would like to use the A form. So let's say that x goes to a. So we do have f of x minus f of a over x minus a. So f of x, which is x plus root x, minus the quantity of a plus root a, and then it's all over x minus a. So one thing that we notice, so this one, we can actually distribute the negative sign. So we do have x minus, well, x plus root x minus a minus root a. And then it's all over x minus a. And don't forget about that. We're taking the limit as x approaches a. Well, obviously you don't want to plug in a here because that'll be undefined. So one thing that we can do, and it looks like this one. Well, let's see. So can we factor it? It looks like it's non-factorable. So what else can we do? So the top part, nothing you can combine because that it's x plus root x minus a minus root a. Another approach is that we can always use the H form. Okay, go back to the previous page. So for the H form, so we do have f of a plus h minus f of a. So let's try to use the alternate form and see what happens. Or the other one is like f of x plus h minus f of x over h. Okay, so let's see. Okay, let me just open it up with the new slide here so we do have more space to show work. So again, going back to the problem. So we do have f of x equals x plus root x. And we need to find the derivative. Okay, so for that one, f of x equals x plus root x. So using the h form, we do have the limit as h approaches 0, f of x plus h minus f of x over h. So this one, so it's a composition, so that means what? X plus h plus root x plus h minus the original functions, x plus root x. So try to use this form, you'll see that something is going to get cancelled here. So x minus x, then that'll be cancelled. And now what's left here? We do have h plus root x plus h minus root x. Okay? So now, once you see the structure like this, so one thing that we can do, we do know that's a radical, so that means we can rationalize it. So the way to rationalize this one, so we can put it into the form, okay, well, let's see. Let's regroup them first. So we do have h plus root x plus h. Okay, let's regroup those terms so we can just rationalize it. So let's put it this way. So we multiply by the conjugate of the top, so then that'll be h minus. Yeah, but that's going to be a little bit weird with the form that we multiply. Oh, you know what? One thing that we can do. Okay, let's see. We can separate them. So something that we can separate, the h over h. Well, obviously that's 1, right? And then the other term, would you have the radical with the h. Okay, so let's try to separate those terms. Yeah, anytime that I deal with something like this, it's always complicated because we cannot use the formula right now. So we have to use the limit approach to find a derivative. So what we can do, so we can set it up like h over h plus the limit h goes to 0, and then square root of x plus h minus root x over h. Okay, so making sure that I come up with the right form here. So it looks like everything is good. And now, this one, obviously, that's 1. And then, but what about the limit here? So this one, we just multiply the top and the bottom by the conjugate. So the conjugate, which is consider root x plus h minus plus root x. Okay, so top and the bottom. So root x plus h plus root x. So for the limit, so this one can be written as x plus h minus x all over h times the conjugate. And one thing that we notice, x minus x, that's cancel. So h over h, so this one can reduce. So now what's left here? So we do have limit 1 plus the limit as h goes to 0 of 1 over square root of x plus h plus root x. Again, there's no more restrictions, so that means we can plug in a number. So h is 0, so this one turns out to be 1 over 2 root x. Oh, 1 plus 1 over 2 root x. So try to put this all together. So this one is like 2 root x plus 1 over 2 root x. So that would be the derivative. And you might be wondering, can we rationalize it? Yes, certainly you can rationalize it. Multiply by root x top and the bottom. So once you multiply by root x top and the bottom, so you do have 2x. And then this one is just 2x also, plus root x. Again, so this one would be the derivative of the original function. Okay, so now let's see what else that we got for the another problem here. So 2.8 going back. So the other one is also radical, so it's g of x is square root of 2x minus 1. Okay, so in g of x, square root of 2x minus 1. Again, using the h form, because that we don't know the value of a here. So h goes to 0, f of x plus h minus f of x all over h. So we'll use that to find the first derivative. So limit h goes to 0, so square root of 2 times the quantity x plus h minus 1, and then minus square root of 2x minus 1 all over h. And for those you might be wondering, so what can I do after that? Looks like this one we can multiply by the conjugate once again. So multiply the conjugate, so that means, okay, let's just rewrite it. So we do have square root of 2 times the quantity x plus h minus 1 minus square root of 2x minus 1. So the conjugate for that one, then that'll be the plus, okay? So let's change the color. Then that'll be considered root 2 times the quantity of x plus h minus 1 plus square root of 2x minus 1. Top and the bottom. And then once you multiplied it out, so we do have 2 times the quantity of x plus h minus 1 minus the quantity of 2x minus 1. Because that's the difference of 2 square pattern. So the radical got canceled. Denominator, we just want to leave that with h times the conjugate, which is what? Square root of 2 times the quantity of x plus h minus 1 plus square root of 2x minus 1. Again, we're taking the limit. We're taking the limit as h approaches 0. So this one, expand it, distribute, combine the like terms. So we do have 2x plus 2h minus 1 minus 2x plus 1. As you can see, that 2x got cancelled. So 2h, well, that's remained. Negative 1, 1 got cancelled. Again, the h, we can cross that out, top and the bottom, because that's reducing. So what's left here, it just considers square root of the quantity of 2 times the quantity of x plus h minus 1 plus square root of 2x minus 1. And again, there's no more restrictions, so what we can do, we can just plug in h. So we got h plus h. Well, this one, h goes to 0. So that means we do have square root of 1 over square root of 2x minus 1, and then plus square root of 2x minus 1. Same terms, combine them, so we do have 1 over 2 square root of 2x minus 1. And a lot of people thought that this one might be the final form, but don't forget, it's a radical form, so we need to rationalize it. So multiply the same radical, top and the bottom. So we do have 2x, square root of 2x minus 1, all over 2 times the quantity of 2x minus 1. Again, what I'm doing here, so just multiply by the same radical in the numerator and in the denominator. And then this one also, we can simplify it a little bit more if you want to, or you can just leave that as a factor 4. So distribute the 2, so we do have 4x minus 2 with the radical on the top. Okay, so now again, any questions, any concern that you have, you can always watch the video multiple times and always fast forward or just rewind to the part that you want to focus a little bit more. So the last slide here, so normally those problems, they're considered the most difficult one. So spend a little bit more time to watch what I have complete here for that derivative g of x and f of x. Alright, thank you for watching the video today. So I'll see you guys next time. Take care.